So, hi everybody, it's good to be here, and I'll be your tour guide for maybe an hour to show you some of the concepts of deep learning. I would strongly recommend that you use this approach rather than trying to learn the APIs first. That was a complete waste of time for me. Thought I was being clever, yeah, too much. So when you see the concepts, the APIs are just the implementation of the concepts, obviously. So just with a show of hands, how many people are basically brand new to deep learning? Okay, how many people have seen my previous presentations? You have? Okay, everybody else, I'm going to tell the same lame joke, so sorry. And so what I'm going to put this, look at this. So here's the thing. The slides are going to be online. This is actually a presentation that's more than an hour. I'm going to give you the 30-minute version. So I'm going to be skipping stuff, but pointing out to things, and everything will be online so you'll be able to see it later on when you have time. And so just a kind of a high-level summary, if you will, of some of the topics that I'm going to talk about. They come in clusters. So usually when you talk about one thing, there's 3 or 4 other things that are associated with it. There's no clear separations. There's not so much linear as more, these are the things that I'll go over. And you see in there I have more hyperparameters, because the ones before them are hyperparameters. I'll tell you in a few minutes what those are. Real quick, this is sort of the overview of different technologies. You don't need to know them to do deep learning, and make a couple of changes. We're going to focus on the red dot parts of that. A couple of things. One, the machine, I can't see here, data science does overlap with deep learning. You can do TensorFlow and Keras through R and RStudio, so if you wanted to. There's also something called reinforcement learning, which is those games, those systems you heard, they play a game 1,000,000 times against themselves. Okay, technically not part of deep learning. They're in there somewhere with machine learning, somewhere on the side. There's also deep reinforcement learning, so just so you know. This first year was last year. So there's home development stuff, home automation, then there's deep learning, and then there's machine learning. That was from last year. Let's see what they do next year. This is the first official event, summer of 1956. The 50s pretty much were when things were starting to get formalized in some sort of way. The fog was clearing. And these are the people who started it. And it even says there at the beginning. One of them is John McCarthy, the inventor of Lisp. Another one is Claude Shannon, who started information theory. Marvin Minsky, one of the giants from MIT. So one of the things they said, which I kind of liked, they thought they'd have it all figured out by the end of the summer. I love that optimism. So just to go into a little bit more detail, I'm going to go back here. You see the 3 circles on the upper right. Traditional AI is about really rules and conditional logic and some data. And that led to, believe it or not, some very powerful expert systems in the 70s and 80s. And some of them still exist. In fact, Google Translate used to use that until they got into deep learning. Whereas on the other hand, machine learning, deep learning, lots of data, lots of inexpensive compute power, lots of algorithms, and of course for deep learning, the neural networks. So this is the thing I'm going to talk about a little bit longer. It's kind of this cold mess of stuff. When you look at it, I know when I first saw it, I got kind of scared, like, what am I supposed to do with this? As you can see, there's a layer on the left, that's the input, and then these things called hidden layers, and then the output. What does that mean? The stuff on the left, you provide a vector of numbers, and they get propagated through these hidden layers, which of course require having numbers in there as well, which aren't labeled. And then at the end, something comes out. So you might be asking, how do you figure out how many hidden layers do I choose? That's not obvious, because it's a hyperparameter. That's something that you set before you do the learning process. The number of nodes, I say nodes, I mean neurons. The number of nodes per hyperparameter. The initial values, for that neural network? Hyperparameters. So you'll be some more that I'll talk about in a few minutes. So let's start by using one technique for initializing it with random numbers from a Gaussian distribution, n0, 1. Then we'll start with just whatever the hidden layers are in there, which are just essentially intermediate computational layers to do the learning stuff. And the goal is to find the set of values for the weights in the edges in order to get a good approximation for the data that you have. Good meaning subjective. And we'll get into more of that in a minute. Now, you notice at the right end there are 4 nodes. I know automatically this is a classifier. A classifier means, is it a bird, dog, cat, fish? Is it spam or no spam? Is it the stock going to go up or is it going to go down? Is it fraud or not? In the case of 2, it's a binary classifier. So there's a class of algorithms that are classifiers. There's another class that's called regression. For regression, that means there's only one output node. So for example, for stock, you wouldn't say, is it going to go up or down? You're going to say, how much will it be? You're treating it as it's a continuous set of values. Not the mathematical sense, because values for stock, there are gaps. But it's almost as though it was continuous. There's also MNIST is another data set with the digits, 10 digits. So there would be 10 output nodes over there. Let's take a look at, and I didn't draw it in, I don't have a slide for this. Let's take a look at an example where it's housing. How many features are there? How many attributes are there for a house? Oh, there's a square feet, number of bedrooms, bathrooms, blah, blah, blah. So try to visualize an Excel spreadsheet where you have each row is data for a particular house. The numbers are the values for the bedrooms and the square footage and all the rest. And then at the rightmost end, it's going to be the value of the house. Here's how it works. You choose your framework, you supply this data that's going to come in on the left end, and it's all those numbers associated with the features, not the rightmost number that's the cost of the house. What happens is you pass in those numbers, does its computations, and then the result, which we're pretending is only going to be one node, is compared with the number that's in the spreadsheet. The numbers are different because we randomized the initial values. So we end up getting this thing called a error function, which is a hyperparameter. And it's based on these attributes that you've got in there, and it's going to figure out how to calculate a number which is based on derivatives, partial derivatives, chain rule, in order to go from the right end backward to update the weights. So when you go from left to right, forward propagation, from right to left, backward error propagation. And one of the other things that's in there, I'll throw in, is called the learning rate, which is a hyperparameter, usually between 0 and 1. So what happens is in the code, you'll have 2 lines of code generally, where you'll have, initially there will be cost function equals something. It's in the framework. And then there'll be this gradient descent choice hyperparameter. And then there's the chain, you do chaining, method chaining. So there's that dot LR, learning rate, you set it to a number, dot minimize, and then there will be the cost function that you had in the line before. Those 2 lines come together very often. Those are the 3 things you need for backward error propagation in order to calculate the new values to update the weights. How many times do you do that? Depends on the data set. Something like MNIST has 60,000 training images. That's 1 epoch. You usually do something, let's say 20. That means 1.2 million times of forward and backward, each time updating all these numbers. And then you have finished with that and you got 95% accuracy. Is that good? Maybe. You take the test data, which is separate, you don't modify the weights in the model, it's locked down, and you just do the forward pass. And then you figure out what the percentage is of accuracy. Then you compare with the training. If the numbers are close, it's probably a good model. If it's not, if it's lower, you probably have something called overfitting, which is like signal, and then there's noise, and a significant part of the noise is treated as though it's part of the signal. That's the general idea. And there are techniques to deal with that. dropout rate, and so on and so forth. Does that make sense? That's sort of it, kind of. You know, the rest is just details. So let's take a look at a simple example. I said we'll do the housing one. That's a regression because you'll have a data set and then there'll be some number. You go, let's predict what the cost is going to be for some house. Does anyone remember slope equation of a line? Y equals mx plus b? It's back to haunt you if you didn't like it when you were in high school. So m is the slope, b is the y-intercept. What that means is something like this. You change b, it's a vertical translation. You change m, it's a rotation. They're two independent variables. So you're trying to say, what's the best fitting line for that data? There are lots of data sets out there that don't fit linearly. We're going to completely ignore all that stuff because we can. And we're going to use the simple ideal case. The idea is to get the line that's the closest to all those points. And what does that mean? One way is to compute the minimum squared error. And the way that works is you see each of those dots, you take the distance vertically from that dot from where it would be if the dot were on the line, square it, nothing's negative, add them up, divide by the number of points. That's the thing to minimize. It's quadratic. It's got two variables, m and b in the horizontal plane. So the cost is going to be in the third dimension. This is going to look like this. This is called a convex surface. And what that means that you'll either have a maximum or a minimum. In this case, it's the minimum. That point at the bottom has a value of m and b. That's the best fitting line. That's how you equate the two. You actually quantify it. So now, let's take two planes, perpendicular to the horizontal plane, perpendicular to the axes. They will intersect in two parabolas that intersect in that bottom point. Why do we do that? Because when you have a parabola, you can take the partial derivative with respect to that variable, set that derivative to 0, that's the minimum. Who remembers differentiation?
Well, it's not enough to be to change the sign from last times.
Sorry? I can't hear you.
So derivative equal to 0 is not enough to be mu.
Well, for the convex surface, it is. That's why it works. There are other cases which I'll describe. So we can solve, we get an equation, closed form, it's all done, great. No, in life it doesn't work that simply. Let's pretend that we didn't know this and we had some random value for m and b. It's going to be on this surface somewhere. Generally, what's going to happen? How will that dot, let's say it's a little tiny sphere, if we were to release it, what's it going to do? It's going to, a little time slice. It's going to go in the direction toward that bottom point. That's gradient descent. Keep that in mind. It's going to come up again. So, as I mentioned before, a house with a, say, number of square feet, very coarse-grained system, you're not going to get a very good, it's going to be underfitting, actually, the opposite problem. Let's add some more features. I've got 6. I actually saw a data set that had 30. Now, here's how the equation is generalized. Instead of the y equals mx plus b line, we get a hyperplane, still linear. Then we come back to this guy. So the numbers on the left, the input values, the input layer, we're going to take those row of numbers, 15, 30, however many there are, and propagate across. It's been initialized. There's one important thing that I didn't tell you. This is linear, which means you can multiply all the matrices together between the consecutive layers, get one matrix, collapse it down to input and output, which defeats the purpose of the network. So what we need to do is add nonlinearity, which is accomplished by selecting something called an activation function, which is a hyperparameter. So by analogy, think of driving on the highway, there's no cars around. You can drive at a constant speed. If you're in a parking lot with speed bumps, you have to slow down and speed up and slow down and all that. So the analogy simply being it breaks up that constant behavior where you can drive all the way at the same speed. That's kind of the idea. If it's confusing, it's okay. It bugged me for a long time until finally it just became clear after seeing it 20 times. So what happens is you have the input values, multiply by the matrix, get a new vector, and pass each of those numbers through that activation function to get a new vector and repeat. That's the extra twist. Does that make sense? Sort of, kind of? Okay. So these are some of the equations. We can kind of skip through this a little bit. The matrices, yeah, this and that. Euler's function. Do you remember, anyone remember Euler's constant? Remember log base 10, and then there was the ln base e, that's the number. And it turns out it's the only non-zero differentiable function that equals its own derivative in the plane, just as a bit of trivia. It's got a lot of other interesting properties. This is the sigmoid function, activation function between 0 and 1. You'll read stuff about squashing the values. Take any set of numbers, positive, negative, regardless of how big they are, pass them through that, they'll all be between 0 and 1. So you're squashing it. Here's another one, tan h or than, hyperbolic tangent. That's between -1 and 1. Look at this one, rectified linear unit. All these are available in all the frameworks. There's ReLU6, which cuts off at 6. That's specific to TensorFlow. And so these are the functions that you can use. Right now, this is the one that's popular. There are other ones as well. We don't need to worry about that. This is this exponentiating the values. Again, it'll do the same thing. You'll get a set of numbers between 0 and 1, whose sum is 1. It's used for convolutional neural networks. So in Python, just if you look at you see sigmoid, that is pretty much the formula that you saw before. Look at tan h. It's actually called tan h, conveniently. And ReLU is the maximum of 0 in that number. Fine. By the way, that point 0 is continuous but not differentiable. Minor little detail there. So some of the, depending on at what point in time that you were looking at activation functions, different ones were in vogue. I already mentioned that ReLU is the one du jour. However, for recurrent neural networks and LSTMs actually specifically, they still use sigmoid and tan h. So don't throw away that knowledge. It's not wasted. It's definitely very useful. Going back to cost functions, here we already saw this. Here's another one. This one's a bit problematic. Why? Because there's that point there where one way it's a minimum and the other way it's a maximum. And there are techniques for getting away from that point to try to get to the minimum. And sometimes it's just, well, I'm not at the minimum absolute, I'm at a relative minimum, but it's good enough. That's another compromise. It depends on the problem you're working with. In deep learning, it's a lot about heuristics and approximation and good enough and slow enough, fast enough, whatever. So it's very much data specific, data dependent, I should say. This is a cross-entropy related one. You can check out the stuff that I mentioned on Wikipedia. There's lots of good entries there, actually. And selecting a cost function, not so important. CNNs versus RNNs. What time is it, by the way? Oh, good. I'm sort of ahead of schedule. So convolutional neural networks, about 60% of the neural networks are CNNs. As of last year, probably still pretty much the case as well. There's some things that you can do, image processing. You can also do audio as well. RNNs, recurrent neural networks, have some issues. It's a cluster of different types of neural networks. The darling of the hour, LSTMs, long short-term memory. We won't have enough time to go into it tonight, but those are the things where you do something like, John lived in France, John traveled in Europe, John speaks French. If you started with John speaks blank, there's no way of knowing. It'd be basically a random choice. So LSTMs enable you to do that sort of stuff, and they work reasonably well. So CNNs, here's the idea. You have an image, and you scan it with a filter, and the filter is built into the application, the framework. You don't have to worry about what's in there. It's generally a 3x3 matrix, and you might pick, say, 16 of them. And each one of those ones scans across, it computes an inner product and a number, and generates a feature map. Why are they doing this? Apparently, our eyes work like that. There are parts of our eye that can detect vertical segments, maybe horizontal, ellipses. That's what it's been based on, that idea. And it does work, except when it fails spectacularly. That's another story, which we won't get to tonight, alas. So you get these feature maps, and then this is how it works. As an example, See the one in the middle where it's got the 1? At some point as you're scanning across, you're going to get to the one on the left with the green. So it's a 1 times 42, and you get a 42 there. Does that make sense? So you're sort of, it's like the tricorder thing, you know, scanning across the body. I want to pick up what's happening in here. And you do all these different filters, and each one gets a picture of something. And as an example, here are the filters to sharpen an image, to do a blur, edge detect, emboss. These are in Photoshop, GIMP, and all the rest. This is it. There's no rocket science involved. So what happens then, after you got the feature map, it's kind of like an image, but it's more like a heat map. And what you have to do is make sure that the negative numbers are replaced with zeros, hence ReLU. So convolution layer, then ReLU, then this max pooling. So you take 2 by 2, typically, pick out the biggest one, and then you get the thing on the right. So you end up throwing away 75% of the data. However, by analogy, compression algorithms, there's lossless and there's lossy. What's JPEG? Lossy. It still works. However, yet another caveat. Put a big asterisk next to this. Geoffrey Hinton, since 2011, has been working on an alternative, off and on, called capsule networks, which have advantages. They don't throw away as much data. They do some better things. They give you better ability to look at superimposed images. It still uses the convolutional layer part, but it doesn't do max pooling. And if I can quote Geoffrey Hinton, the godfather of deep learning, he said something like, the success of max pooling has been a disaster for convolutional neural networks. Obviously, it bothers him a lot. And he's come up with this other technique. It's more complicated, but it helps with things like adversarial networks, the things that you can use to fool systems that try to figure out what's in an image. Self-driving cars, they use CNNs, so that's obviously important. Here's an example. Who's worked with Keras? Good. Oh, you already know this. So look what we have here. Model, importing sequential, that's just a container for layers for a neural network. Look what we have down below. Dense, that means it's fully connected. Dropout, I mentioned that. Oh, flatten, activation. Conv2D, max pooling, add a delta. That's a particular optimization technique, the one that I was mentioning. It's a hyperparameter for gradient descent. And look what happens. Input shape, it says there's 3 images of 3 by 32 by 32. The 3 is RG and B. Then number of classes 10, it's the MNIST example. You're going to classify, there's an image coming in, it's one of the 10, what digit is it? And then you start the model. Look what we do. Add conv2D, 32 of these 3 by 3 filters, padding, I didn't talk about that, no big deal. Input shape is up there. Activation ReLU, conv2D, activation, max, you already know what it's doing. That's why, oops, some people really like Keras because it's a lot more intuitive. And no, sorry about that. The best part, right? How's that? No? Can you hear me now? No? Can you, I told you it was the hardest part. Good thing, can you hear me now? Good. Good thing it's not surgery. Anyway. So, TensorFlow, you know all about it, you've heard about it, 4 times as many stars as the next closest one. And, you know, trade-offs. It's lower level. You don't have that facility that you saw. They're adding more of it, but it's still more to the metal, I guess you could say. So it has support for these different languages and devices, CPU, GPU, and so forth. You've probably already seen that. You can visualize stuff with TensorFlow. I can't show you TensorFlow because I was doing some updates last night. It was late, and I hosed my system, so I have to reinstall a ton of stuff. Serves me right. But it gives you a graph, and then you can see the error decreasing and the accuracy. It's a lot of stuff you can do. A lot of good visualization. It's one of the unique things about TensorFlow that isn't available in some of the other ones. Here's the usual suspects for use cases. Pretty much what you expect, it can do it. Now, some of the aspects of it has to do with these things called tensors, which are multidimensional arrays. And it creates a graph. So you have nodes and you have these tensors, so you have operations, and it's all deferred, which is trade-offs. There's actually eager execution introduced in 1.4, part of the mainline from 1.7. And it looks more Python-esque, which they're doing with other things to decrease the impedance mismatch so you don't have to go back to Python and TensorFlow because you're crossing boundaries for processes. So they're making it Python-esque inside of TensorFlow. Anyway, is anyone familiar with I think you are, an AST, abstract syntax tree? You can sort of think of it as a graph in TensorFlow is like an AST on steroids. It's got a whole bunch of stuff that's happening. So what you have to do, this is a little strange, maybe, when you first see it. You get this session object and you invoke the run method, and in the method you specify the thing that you want it to compute. Not exactly intuitive. So I'll show you in a second. And you have the dimensionality of the tensor corresponding to different dimensions of something. Like, for example, a constant has 0 order. Then there's vector, matrix, 3D. Usually you don't go higher than 4D. I think I met a company, they're doing 5-dimensional tensors. Kind of unusual. So here's an example. There's constants, placeholders, and variables. I won't go into the difference between them. No big deal for tonight. But just as an example to execute something, we have a constant, we print it, tf.constant. This is the sort of idiom. Import TensorFlow as tf. TF is always TensorFlow. They basically co-opted it. And when you print it, you get the metadata. You don't get the value that's actually assigned to the, meaning the 3. So here's what you do. Sess equals tf.session, print sess.run the constant. Remember, which is what I just said a minute ago. And then it'll give you the value. Intuitive? Hardly. Here's one that saves you a line. With tf.sess as sess, print that. Still. We'll look at eager execution in a minute. Here's some arithmetic stuff. Add, subtract, multiply, divide. It gives you what you expect. Here's some other stuff. We've got pi and approximation. What's the sine of pi radians? 0. What's the cosine of pi radians? -1. What about sine of pi over 4, cosine of pi over 4, tangent of pi over 4, tangent of 45 degrees? Everybody remembers? 1. So let's look at the values. Oops. We said 1, we said -1. What about this other number? Some approximation. So just FYI, in case you're doing with scientific stuff, be careful with that. Or you want to make sure that it's within the acceptable range of precision. That's basically it. So now look what we have. A, B, and C. What is C? It's the product of A and B. A and B haven't been initialized, so you can't calculate the value, except by using this feed dict. Sets A and B, and notice at the bottom, print sess.run of, and we specify the feed dict, and it computes it. Does that make sense? Kind of, sort of? That's how it works. This is what you're in for when you really go a deep dive. So now what do we have? An example. We have W is this, it's going to be a one-dimensional array. X and B. Look what we have, WX. That's W times X. What's Y? WX plus B. What's that? The generalization of Y equals MX plus B, the line, it's the hyperplane. This is linear regression in TensorFlow. That's how you do it. That's how the frameworks do it. And so then here, you see you have the feed dict specifies X, the second one, X and B, because those are the numbers it needs, the values of the variables that it needs. Okay. When you want to save a graph in TensorFlow, I showed you in red, that's what you add to the code. Then you run TensorBoard from the command line, which I can't do. And then, did I put it in there? Yeah, TensorBoard dash logdir equals. And that's the directory where there's going to be some TensorFlow graph stored on the file system, and then it'll generate, it'll be in a web page. 6006, which if you invert it, what does that spell? Goog. just in case you were wondering. That's how they came up with the number. It wasn't random. Eager execution looks more like Python. So it's a lot of the functionality in TensorFlow is available. Here's an example. X is 2 dot. It's an array. So it's one-dimensional tensor. M is the mat mul x and x. Print M is 4. So it's more Python-esque. And it's in the mainline, I think it's either 1.6 or 1.7, and the latter came out about a week ago. So it's fine, if that's what you want to do. Here's some examples. I'm not going to go into the detail. Some of the code samples, that's the link for the GitHub repository with this code, and there's a link down below for LSTM, TensorFlow, and Spark. I'm going to show you just the first one, linear regression. I'm not going to go into a lot of detail because I'm running out of time. For one, you remember I said that in order to do backward error propagation that you need 3 things? Do you remember? It's okay if you don't. It was the gradient descent thing that you choose, hyperparameter, learning rate, another hyperparameter, and then the cost function, which they call optimizer. So do you see those lines in blue? Can you see them? I can't. Let's see. Where is it? I can't. Oh, there's Zoom. Okay, great. Oops. See those blue lines? Mat mul inputs and weights. These are the predictions. We're predicting stuff. Loss, cost. The sum of the square of the difference of the predictions and the outputs. I've skipped the first part. Remember what I was saying about summing the squares? That's that. And then train operator, you could say. TF, transfer, train attograd, that's the gradient descent method. There's 5 or 6 of them. To dot minimize, remember I said minimize the cost, which is the loss. There you have it. That's what that means. If you can figure that out without ever having seen any of this stuff, you're a lot smarter than I am. Because this is gobbledygook when you don't know what these APIs are about. Does that make sense? Kind of, sort of? Remember, if you're like me, after about the 20th time, it becomes, oh yeah, this is, sure, it makes all sense. So, just a comment. How much time do we have? You need 20 minutes? 15 minutes? Okay, a little sort of side thing. Yeah, I hope so. So, all this stuff with deep learning, there's a lot of discussion, there's hype, there's not as much as blockchain, but there's all the, is it real? Is it fake? What's the story? Some success, but maybe it's a lot of fluff. Who knows? That's a fair question. I want to say one thing about that, 2 things. One, there's something called the universal approximation theorem. Has anyone heard of that? No? 1. It states that any continuous function in the plane can be approximated arbitrarily closely by a neural network. The differentiable functions there's lots of them. They're a subset of the continuous ones. Remember ReLU? It's got the kink in there? It turns out that there's an uncountably infinite number of continuous functions in the plane, each of which can be approximated arbitrarily closely by a neural network, which tells you the expressive power of neural networks is immense. You may not believe that. That may not make much of a difference to you. Here's another thing that happened last summer. A startup created a barcode scanner for blind people. And the one before their product was $1,300. Theirs was $20 using deep learning. And that's all it did, was to scan and you can't expect much for 20 bucks. So after a while, it turns out that this little barcode scanner started reading the dietary information on the labels, like the ingredients and the percentages. No one had trained it to do that. No one expected it to do that. No one knew. How could it possibly do that? Well, my answer is simple. That's the power of deep learning. It's kind of a feel-good story in a way, and if you've got that kind of nihilistic, we're all doomed sort of style of movies that you like, which I do, I can hear the voiceover. First it was the barcode scanner for blind people. And a month later, Skynet 2. And my answer is, I'm not worried. So other than that, what we're going to do, I think we're just on schedule here. There's an example of a Docker container with those technologies in there. Those are the version numbers. And Khan is going to take over and show you some of the things that you can do with that. And I think it's interesting. So take it away, Khan.
I've got like 15 minutes, I think. So I don't think I'm going to be able to cover everything, but I wanted to talk a little bit about the Scala API for TensorFlow. So this was developed by a individual who's a PhD candidate. His name is Platinos. There's the link for that. It's fairly easy to put in your SBT. There's a little bit of a hitch because it's dependent on the C API for TensorFlow. So you either have to custom compile it in Bazel, or there is a jar file that he releases with a snapshot that is specific for OS X or Linux. So that's just one of those things you need to be aware of. So the documentation is really limited because it's one guy trying to do all this stuff. So he's got the APIs for tensors, learning, and core. So tensors are pretty simple, and they're very similar to NumPy. So anybody who has worked in Python, you're going to be pretty familiar with how to structure the tensors. Learn is similar to Keras. So this is, again, it tries to mimic Python for a lot of people who are most familiar with that. The core level stuff is for the people who really want to dig down deeply. So it's good, but there's not a lot to do. This isn't really, in my opinion, really prime time. But it's an interesting project, and I think it it merits some exploration. So importing that, this is very simple text. I mean, this is how it looks. You can probably mistake that for Python. Of course, the advantage of Scala is static typing, but inferred, right? So you can see that, that's no problem. We're going to explore a multi-layer perceptron for the MINST. Everyone's familiar with that, right? The letters and how to identify X, Y, Z, whatnot. You import. Pretty straightforward. We're just importing that data set, downloading it, shuffling around in batches. So this is where I'd like to borrow from Oswald's slides for a moment and kind of specify something. This slide here, when he's talking about that, this is a fully connected feed-forward network, right? When we're doing things like convolutional neural networks, those are also feed-forward, but they're actually not fully connected. Usually we have this right here, the final layer, which is fully connected, but the rest of them are not. And so you're going to see why we need that reduction. And the advantages of that, that's pretty much nothing. Sorry, I'm going to go through this a little quickly. So this is kind of the meat of creating the tensors. What's important to note is you see here, he was talking about activation functions. Here, we're using ReLU. That is pretty much standard. There's something called leaky ReLU as well. But for CNNs, ReLU is pretty much it. TANH you can still use, but I don't think, sigmoid, it's pretty slow. I don't think anyone really is going to use that in a practical way. So the layers themselves, as you can see here, are reducing. And this is where Oswald touched on max pooling. To that. Well, let me show you this. So what we're really doing here is we're sliding across this image, and we're reducing each layer by a certain amount. So we're moving this way, we're taking this square, we're taking another square, and it overlaps so that we can preserve dimensionality within those layers. Eventually what happens is you go here, and then this is where, again, I said we have fully connected layers. And right here, usually, is where we're using softmax. Softmax is a function that translates everything to a sum of 1. So it's easy when you see here the labels of bird, sunset, dog. You're going to have a percentage, and they're all going to sum to 1. So the likelihood that it's a dog versus a bird, you're going to see that difference. Here again is the max pooling. So when we take, this is the dimensionality reduction, where we're taking this, and we're just taking the max from each grid. What's interesting about this is, so in standard CNNs, you see the reduction, but when we're doing something like RCNN, where it's regional CNN, actually we reduce and then we go back out. So it's kind of, you get a lot of layers. That's let me get back here. So we're going to create that. I'm going to skip. OK. So again, this is something that was touched on, but gradient descent for backpropagation. There's multiple techniques right now. I mean, standard gradient descent is OK. You can play around with decay rates if need be. Stochastic gradient descent is kind of, it's pretty good, but one other feature that they've done is that it's called stochastic gradient descent with binning. And what happens there is you actually bin the data, and it's actually faster. The technique with stochastic gradient descent is it is actually noisy because it's stochastic. So, but what's interesting is with binning, it's actually faster and more accurate because you're just taking chunks of the data, and it's highly parallel. So that also helps with the speed. There we go. For this example, though, we're actually just using gradient descent. A lot of code. I want to go back to this for a second and talk about the backpropagation. When we're doing that, this is where I think Oswald mentioned that you're going to see kind of the networks train themselves. This is where it's very important, the technique with stochastic descent, gradient descent. But what's interesting is that there's a lot of risk of overfitting. And typically what you're going to do with this is you're just going to drop 50% of your layers in the network. And what's going to happen with that is it's going to force the network to find a different solution to the final layer. Let's see. So with that, the code is pretty much straightforward when it comes to how you're triggering it. You have this is lazy because this is a DAG. TensorFlow 1.7 has the eager execution, but this one is still lazy, and the Scala I don't think has caught up to that yet. So you're not going to be able to do that. We're going to do some, so we can show. You can see here we're doing max steps. We're doing for about 100,000, and then let me go show you here. Code, which sucks. Okay. View. All right. Whole lot of code. So you can see here that it's processed at the eminence. We're downloading a lot of data, and then we get to the evaluation and training right here. As I said, we've created all these layers. Eventually, what you get with the softmax is you get that recommendation based on, whether it's a bird or a cat or a dog, and the back propagation is not that accurate for this one. Unfortunately, I didn't get the final piece of code running, so yeah, that's it. Okay. So anyway, I guess that's it. You guys have any questions for me, or where's Oswald? Is he? Okay. Yeah, go ahead.
You're going to touch on the Scala with Spark, and that's part of it.
Oh yeah, I'm sorry about that. You were waiting for that? So there's a couple packages for that. One of which is TensorFrames. Have you explored that at all?
No, I'm currently looking for the TensorFlow on Spark with Yahoo provider. I'm just to see how you view the overall integrations with different frameworks.
So so there is the TensorFlow on Spark. I think TensorFrames is actually interesting, although there hasn't been a lot of development lately on that. But it's actually a DSL, for the Scala language, and so it allows for a lot of flexibility, and working. It's based on protobufs, so. I think that it's a good solution. I think they stopped developing it really when there was tensor serving and those solutions like that. Any other questions? Me or Oswald? Good.
Where did you say you teach?
You see this C, it's a Santa Clara. It's, just so you know, it's 1 night a week, 10 weeks, 3 hours, Friday nights, 6:30 to 9:30. Yeah.
Go slugs.
Any other questions? All right, I'll post the link for the slides probably later tonight. We'll do that. Thank you very much for